So at the end, the U is chi0 to the -1 minus chi to the -1. So we basically construct this matrix, and the diagonal part is going to be the number that we need. Okay. How do we do this in practice? You will see this afternoon. But first, you run a self-consistent calculation with no perturbation. Okay, you get the potential, you get the ground state wave function of your system at the DFT level. Then you start applying this alpha perturbation, the perturbation in the localized potential acting on the D states, and you compute. You use the wave function and the potential from the self-consistent solution, okay, to start the perturbed calculation. And you do this for a series of alpha around 0, basically, because you want to construct these derivatives. Okay. Now, at the first iteration of the perturbed run, you get the chi0, because you have that the electron-electron interaction has not yet come into play to screen the external perturbation. Okay, so the system behaves like a non-interacting system having the same density of the real one. And at self-consistency, instead, you obtain the derivative that will produce chi. Okay.
This is how the assumption is that we are in the linear response region, right?
Yeah.
But in reality, it is not always like that. So there will be some correction on the topic.
No, I mean, we normally work with small values of alpha, and we check that we are in the linear regime. So there you will see that the dependence of n on alpha is usually linear. So we will check this afternoon, and you will see straight lines. Okay. So there's a number of advantages in using this calculation. First, because first of all, it's a completely ab initio evaluation, so you don't need any guess. In literature, you find often papers where they fit a U until they reproduce some properties, and then they use that value for the calculation. But of course, that is not good enough, because if your system changes phase, changes polarization, magnetization, and things like that, and in principle U changes as well. And it's not easy to account for that effects if you cannot measure it. Second of all, it's consistent, fully consistent with the approximation you start from and with the approximate DFT functional you aim to correct. So say that if you start from LDA or GGA, it's going to make a difference. So you're going to obtain a different number for U. Also, it's consistent with the definition of the functional, and in particular with the specific choice to describe localized orbitals. Say that you want to use Vanier function instead of Gaussian, instead of atomic orbital. You could do the same thing, okay, and obtain in general different value of U that would be good for that function built on Gaussian, for example. And it's easy to implement, easy to work with this method, because if you have, especially if you have an LDA+ implementation in your code. I'm gonna just stress, this is a quick slide, there are a few slides with which I try to convince that U should be recomputed consistently, say with the structure. Say that you're in this paper we were trying to reproduce, for example, the properties, the structural deformation of iron oxide under pressure, and we obtained this solid line quite good agreement with experiment, only recomputing the U at different volumes of the unit cell. Same thing here, where instead they were studying the spin transition in magnesium iron wustite. Okay, so they could obtain a pretty good estimate of the transition pressure, but they used say a volume of pressure dependent Q.
Oh, what does HF and RF mean?
This is high spin and low spin. They were comparing the two phases of the material with zero magnetization, basically S equal to 2. And as you see, the U depends on the magnetization as well. So everything that changes the electronic structure of your compound probably is reflected on a different value of U. Okay, these are some details about our calculation, but it's not needed. This is the last work that you may want to check where we found that recomputing U for a different structure actually gives a better estimate of the structural properties, the equilibrium structural properties, the bonding properties, say, between cobalt and oxygen. I guess it's in here. So something that you may want to check. Now let me just rapidly go through one particular development of what I said so far. That is a self-consistent calculation of these parameters. So sometimes it turns out that the ground state that you obtain, that you stabilize with a U, is even qualitatively different from the one that you have with approximate DFT function, so without any U. So in principle, in those cases, you should compute U from a DFT plus U ground state, okay, because this is what the function would correct, okay, when you use that particular value of U. And this can be done generalizing the calculation of U I was showing before in this way. So now you, when you apply the perturbation, this alpha times the occupation of that particular site, you start from a DFT plus U correction, a DFT plus U function. So it's not DFT only anymore, but it's a DFT plus U. Still, you want only the response of this part in terms of second derivative with respect to Ni. So what one can do is freezing the potential coming from here. Okay, and this can be done by just fixing these Ni's. When the code constructs the potential before diagonalizing the Hamiltonian, you make it use the occupation that you got from the self-consistent run. Okay, so there's no contribution to the second derivative of the energy coming from this part. Okay, so the only part that contributes to that is only the first one. So you'll be measuring the usual U as a second derivative of the function that you aim to correct, but from a DFT plus U ground state. Okay, this is we use this some approximation to this, an equivalent algorithm, but done differently in this calculation where we were measuring we're studying this chemical reaction consisting in we had an iron oxide dimer. We want to study the addition of hydrogen there, how it creates water at the end. Okay, so you have hydrogen coming in, attaching to the iron, and then eventually forming a water molecule with the oxygen that leaves the iron alone at the end in here. So the black lines are for CCSD kind of calculations, so quantum chemistry calculations that are supposedly more accurate for these small systems because they explicitly take into account the many-body nature of the wave function. And as you can see, the GGA doesn't compare very well with the result of the CCSD. Has some problem that not reproducing very well the spin crossover at this state, and also the barrier for the back reaction is not well reproduced. We could obtain a much better agreement to the CCSD results with these consistent U. Another example is on this other molecule, the in molecule, that we wanted to study. For this molecule, we wanted to study the magnetization of the iron atom at the center, with and without the diatomic molecule attached to it. And as you can see, was only with this consistent Q that we could reproduce, at least qualitatively, the results of the experiments. No other approximate function could obtain the same agreement. So, well, I think this is the end, the last slide of my presentation. I just wanted to point out some possible future extension, like the calculation of that J parameter that we have neglected so far, and the use and its use in an extended functional. Also, we're working on introducing intersite electronic interaction. So far we only have interaction between electrons that are on the same atomic site. But the other model, the extended other model, also has interaction between sites, and one would see that with these intersite interaction included, also system like silicon could be described better, like having a more accurate estimate of the band gap, for example. This is another problem that I haven't touched here. I mean, double counting, there are different flavors of double counting in literature, and they're not equivalent to each other. So people say that different double counting are needed for different sort of materials. Say if you have a bulk transition metal, then the schema I've presented is not good, and another formulation of the double counting would be needed. But this is an uncomfortable kind of situation. We would like to have a function that is good in as many possible cases without changing anything. Okay? And this is a refinement that's needed to obtain full covariance of the method. So you don't want that your result will change if you use either Barnier function or atomic orbitals. So you want a functional that will stay the same even though you use another basis set to calculate your projection, so your on-site occupation. And that's only possible if you generalize the formulation of the functional to get a fully covariant one, which is not. I mean, the one we have so far is covariant with respect to, say, mixing of atomic orbitals on the same site. But what if I mix the orbitals of different sites? Then this functional wouldn't be the same, so it would change, and that's not good enough to have a general formulation for the correction. And of course, the fact that we have to compute the parameter in a separate linear response calculation is not very comfortable. We would prefer to have some hopefully simple and not expensive scheme to compute it at runtime, so we don't have to worry about all these separate calculations. I mean, those are all things that we're thinking and we're working on, so hopefully some improvement will come. Well, this is what I have to say. So if you have any questions, I can take now, or we can have a break before the second part of the morning lecture.
So is there any way to compute spin-on or spin-wave dispersion?
What do you want to compute?
Spin-wave dispersion? Can you kind of compute like spin-wave, like the energy and the vector relation?
Spin wave, you said?
Yeah.
So we localize moments.
Yeah, like say yes, spin-on or spin-wave.
Magnons.
Yeah, magnons.
Magnon
Yeah.
dispersion relation.
So I mean, this is a general question, not exactly related. I mean, not specifically related to what I I presented here, you can think of something related to what you saw yesterday, for example. So instead of having a wave in the position of atoms, you would construct a wave in the spin, provided that you have, I guess, that's what you're looking for. You have a localized momentum, okay, on the atoms. Also, you need probably a non-collinear description of them, because you want finite change, I guess. That's what you're looking for of the momentum. Maybe you want them to turn with respect to a specific direction in the crystal, and you need all these characteristics to be built in your function to start with. Then you're not done. I mean, you have still to construct the linear response machinery that allows you to say compute monochromatic perturbation separately, like you saw for the phonons yesterday. Yes.
From the LDA plus U, do you actually get the spin direction more than just up and down?
No.
You still don't get it, right?
No, I mean doesn't change that part of the function.
Okay, so that's where you said Dirac equation or something else maybe.
Yeah, yeah. You would need to implement these in what you would see in this lecture, in a more general function.
So how can we use the value of U? For example, if I get the SCFU like 5 electron volt, but if I want to use other software, then but usually other software requires U and J. So in that case, how I
So these the U that you compute this way with this functional is U minus J. So is the effective U.
That's the effective U.
Yeah. So unless you compute U explicitly or J explicitly, you don't have a precise idea of what. But if you have another software, the best thing is to use the other software to implement this method and recompute everything consistently. Because you're never sure that the details are the same, and maybe the basis set changes. So, or if the other software is based on mapping in orbitals, then the same value is not good.
Is it implemented in plane waves or Pt2?
These in plane waves. I don't know actually about the Pt2, so I don't know if there is any implementation of the U on the Pt2. Does it make any difference?
I think shouldn't change, but I don't know actually.
Not sure.
There are also classes of material which are electrorestrictive material and magnetic-restrictive material. And then you look at them by using quantum separation. Like for example, in optical fiber, electrorestriction is very, because silicon dioxide is there, which deform and they dipole and because of electric field they shrink. And when you are down such electrorestrictive and magnetic-restrictive material using quantum separation, I don't see any paper on it.
I'm not sure. Not that I know. Yes.
Some more general. Does one need to add Lasky correction during the pseudo-potential contraction as well?
No. This is done at the level of the calculation in the.
Do you expect this to change?
There was one paper by actually in the group of Nicholas Spalding, from the group of Nicholas Spalding, trying to modify the pseudo-potential based on this. I don't remember the details now. So it's from, I guess, from 2003.
Is there an issue of double counting there, like counting correct for the same thing? Or
Sorry?
would you expect it to be accounted twice for the same effect? If you change the pseudo.
Let's see. Not. totally sure that is really possible. And what they were trying to implement is also something else, something slightly different, because I mean, the details of the band structure depends on the material. It's not something that you can compute. Also, it's a many-body effect that you're trying to build. You know, so I wouldn't know. I would need to think of it. Any other question? Okay, I would say we have a break now.